Hello, everybody. Many thanks to the organizers for giving me the opportunity to be here. I'm pleased to talk about my work on representable functionals for a class of locally convex quasi-star algebras, namely for the normed case. Let me start with some motivations. Mathematicians have tried to describe in a rigorous way quantum systems. And for these reasons, observables are considered as elements of assisted algebras, and states are given by positive functionals. Unfortunately, some quantum systems require representations of observables through unbounded operators. So unbounded operators are only densely defined in general, so only a partial multiplication can be defined. For these reasons, partial star algebras have been introduced, and in this talk, we will focus on a special class of such objects, namely on quasi-star algebras. Quasi-star algebras are algebras of unbounded operators, and examples are given by square interval functions over, for example, a compact interval of the real line with the Lebesgue measure, over continuous functions over the same interval, and or over essentially bounded functions. We are interested in representing such algebras or quasi-star algebras in concrete families of operators. So for this aim, we want to look at representable functionals. Representable functionals in general might not exist, might not be continuous. So it's interesting to understand the continuity for such functionals. In 2017, we were able to give a positive answer in the sense that for commutative Hilbert quasi-star algebras and under certain conditions, every representable functional is continuous. So let me start with some reference. So what I'm going to tell you today is on this third paper, is a joint work with my supervisor, Camillo Trapani, and the applications are contained in the two papers with my supervisor and Maria Fragolopoulou from Greece. So let's start with the definition of a quasi-star algebra. So it's a complex vector space A, and A naught is a star algebra containing A. We have a multiplication, a left and right multiplication that is defined only for elements of A and A naught. And we have a sort of associativity property and an involution that is a natural extension of the involution in A naught, such that such properties are verified. And these are very natural properties for our quasi-star algebra. So let's jump to the definition of a representable functional. So just keep in mind that this is a counterpart of a positive functional for a C-star algebra. So we require the positivity condition, but only for an element, for elements of A naught. Recall that A naught is a star algebra. The second condition gives you invariance, and the third condition is a sort of continuity condition, but observe that the constant gamma of A depends from the element. So now that we have representable functionals and we have quasi-star algebras, we want to understand in which family we want to represent such quasi-star algebras. So bounded operators are not suitable anymore, and we introduce such family of closable operators such that these conditions are verified. So such family is a natural vector space with the natural operation of sum and multiplication by a scalar. Moreover, it's also interesting to consider all the operators X such that X and X star leave the invariant. If we defined the involution dagger and the partial multiplication in this way, wherever these conditions are verified, then we obtained a partial star algebra. And this is the good family where we want to represent our quasi-star algebra. So the star representation of a quasi-star algebra would be such a map. for which the involution is preserved, and also the partial multiplication is preserved whenever this expression will make sense. So the reason why we call such functionals representable is because for every such functional, you can construct a closed cyclic representation, star representation, and a cyclic vector such that this formula holds. Closed and cyclic, I'm not gonna define them, but you might think in a similar way as for the case of a sister algebra. But the main point here is that for every omega, you can find a triple of a star representation of a coset map and a Hilbert space, such that this formula, this equality holds. So now we have defined the algebraic context. We want to understand which kind of topology we want for our quasi-star algebra. So we start with a locally convex topology tau, such that the multiplication is only separately continuous, and then we require it to give continuous involution and continuous right multiplication operators by elements of A naught, and we also want the elements in A to be approximated by elements in A naught. Since the involution is continuous, the right multiplication operators, the continuity of such operators implies the continuity of also the left multiplication operators. So now I guess it's a good time to give us some examples. So we start with an example given by operators. So we consider the bounded part of L dagger, namely all the operators X such that the closure is bounded. And if we endow the family L dagger DH with seminorms, with the topology defined through these seminorms, so namely with the weak topology tau W, then we obtain a locally convex quasi-star algebra if we couple the family with L dagger D, with the bounded part of L dagger D. Another interesting example is given by the Schwarz space with the topology given by this seminorms. And if we look at the dual of tempered distributions, then we obtain another locally convex quasi-star algebra. And the partial multiplication is given just right here. So these are locally convex quasi-star algebras examples. Let's jump to the Banach case. So we start with a von Neumann algebra and the normal faithful semi-finite trace on the positive cone, and we consider this ideal. We complete it with the norm defined in this way, and then we obtained a Banach quasi-star algebra if we consider the intersection of L infinity and LP. So in this case, L infinity is just the von Neumann algebra, and the completion of the ideal GAP with the norm. If the trace is finite, then we don't need to take the intersection, and we obtain again a Banach quasi-star algebra. So a Banach quasi-star algebra is a locally convex quasi-star algebra for which the topology is just defined by a single norm. Of course, L2 spaces also fall in this case. A very special example of Banach quasi-star algebras is given by Hilbert quasi-star algebras, and in this case, the norm is also coming from a inner product. So we really ask the same requirements, but this time we have a richer structure given by the inner product. So if we just take the completion of A naught with respect to such topology, then we get our Hilbert quasi-star algebra. So we have given some examples for quasi-star algebras, and now it's a good time to give examples of representable functionals. So consider A naught as essentially bounded functions, and endow them with the P norm for P greater or equal than 1. If you complete L infinity with this norm, then you obtain the space LP. And if you consider P greater or equal than 2, so this time we we forget all the values between 1 and 2, and we consider an element W into L infinity that is non-negative, then the functional defined in an integral way turns out to be representable, but it's also continuous. So now that we have introduced our background, we want to study such functionals. A good way to do that is to study Sesquilinear forms associated to W, and these are defined in this way. So this can be defined for elements of A naught. And the question is, can we extend them? Can we study them also for elements that are not belonging to A naught? These functionals turn out to give a closable Sesquilinear form if they are continuous. And the closure is defined in a very natural way as the limit procedure. And these are densely defined because this domain contains A naught. So the question is, can we go further? But first, let me introduce some notions. First, I want to talk about fully representability for locally convex quasi-star algebras. So we ask the family of representable and continuous functionals to be sufficient, and the domain of all the Sesquilinear forms to be, of the closures of the Sesquilinear forms to be the whole A. Of course, this is the most difficult condition to verify usually, rather than this one. But we were able to show in 2017 that for the case of a Banach quasi-star algebra that is unital, then the second condition is always verified. So this means that for Banach quasi-star algebras, this condition doesn't appear anymore. So a Banach quasi-star algebra, which is unital, is fully representable if the family of representable and continuous functionals is sufficient. In fact, we don't know if representable functionals actually exist, in the sense that there are examples already in the Banach case, for example, for p equal to 1, that admit only the trivial functional as representable and continuous functional. So full representability tells you that you have enough representable and continuous functionals so that you can separate the points into the positive cone of A. Namely, this is defined as limit of elements of the positive cone of A naught. So this would be just limit of elements in A naught plus. So full representability is really close to star semi-simplicity. So in this case, we change our point of view and we focus on Sesquilinear forms. So in this case, we suppose that Sesquilinear forms are already everywhere defined. So these are positive, we have similar condition of invariance, and they are continuous with norm 1. So a Banach quasi-star algebra would be called star semi-simple if this condition implies, so for every omega implies A equal to 0. So I have given the definition for the Banach case, but this can be extended to the locally convex case. So the question is, which is the relation between star semi-simplicity and full representability? In 2017, we were able to show that these conditions are equivalent, but under the condition of positivity. That tells you that if you have an element A such that omega of A is always non-negative for every representable and continuous functional, then A is positive. A class of examples that is always fully representable and star semi-simple is given by Hilbert quasi-star algebras. So somehow we have seen that Hilbert quasi-star algebras behave very well, and we want to focus on this family because the structure is rich, and we want to understand how we want to understand better representable and continuous functionals. So first, I need to introduce what a weakly positive and bounded element is. So essentially, we look at the the multiplication operator, L of psi. If this operator is positive, then we call the element weakly positive. And if the left multipliers is the whole H with respect to this multiplication, then we will call the element bounded. So we're able to show that if omega is representable and continuous, then there exists a weakly positive bounded elements that represents omega, but also the vice versa is true. So if omega is of this form, with eta to be a weakly positive bounded elements, then will be representable and continuous. So from this theorem, immediately follows that every quasi-star algebra H A naught is fully representable. We have actually a strange phenomena in the sense that if we just focus on the case of LP spaces over, let's say, L infinity for X, for mu, enough regular measure, and X finite measure space, then what we have is that for P greater than 2, we have plenty of representable functionals. Indeed, LP is fully representable. For P less than 2, but greater or equal than 1, then what we have is only the trivial representable and continuous functional. So we have this big gap between what happens before for P less than 2 and P greater or equal than 2. So the question is natural. Is every representable functional on a Banach quasi-star algebra continuous? We have tried several approaches, but first I want to give you an example of a continuous functional that is not representable. So what we do is we construct a functional that is positive on A naught. It satisfies the invariance property, but it doesn't satisfy the third condition about the existence of a constant. So we consider P equal to 2, the same setting as before. We take H non-negative, and then we define our functional in this way. To get the desired example, just take H to be in L2, but not in L infinity. So as I said before, we have tried several approaches to study the continuity problem. And the first one is to look at positivity. We have seen for C-star algebras that positivity plays an important role. So first we need to introduce the concept of integrable Hilbert quasi-star algebra, and also I need to introduce this module function. But if you wish, you can think of this module function as an absolute value. So it's a function mu from the Hilbert quasi-star algebra to the sorry, this should be omega plus w. With the following properties. So the image is contained into H plus of omega, so the set of weakly positive elements. It is the identity for such elements, and it is isometric. Then the reason why we have introduced positivity, weakly positivity, is because already another notion of positiveness has been introduced, in the sense that every positive element is limit of positive elements in A naught. And under the condition that the Hilbert quasi-star algebra is integrable and has a continuous module function such that this condition is verified, then every positive element is the limit of a sequence of elements in A naught, and every omega which is positive is also continuous. The problem is that how can we show that a functional is positive? Because every element in H class is limit of elements in H plus, in A naught plus. So if we don't know anything about continuity, it will be difficult to deal with this condition. So this theorem is very nice, but it's difficult in principle to verify this condition. So we have changed our approach, and we will look at an order, we will define a partial order on the family of representable functionals. So I guess that there should be no C here. So what we do is to consider theta and omega, and we will say that theta is less or equal than omega if this condition is verified. Recall that this Susquehannian form is always well defined because omega is representable, so it has a star representation associated to it through the GNS construction and a cyclic vector. So the following statements are equivalent. So every representable functional will be bounded if we can find a non-zero representable and continuous functional such that this condition is verified. The problem is that this theorem is not constructed. So we don't know how to construct the functional theta. So we have changed our approach, and we have looked at concrete examples. So the first examples to consider is L2 over for a compact interval I and the Lebesgue measure over the continuous functions. So in this case, we have moved the problem of continuity to another operator T that maps from L2 into this mysterious space that has been obtained through the Ritz-Markov representation theorem for functionals on continuous functions over I, and this operator T satisfies the following conditions. And these conditions are important because we can use the theory of intertwining operators and use the automatic continuity results that are known for such operators, because you see, T is intertwining the multiplication operator by phi. And this allows us to show that every representable functional omega is actually continuous. Moreover, we also have some information on the measure mu. A similar result holds for the case of L2 over L infinity, but in this case, we have to use results that are known for functionals over L infinity, but the application is the same, and everything is regards all these properties 3 and 4. These results can be generalized a little bit. The main idea is to find this operator for which we move the problem from omega to this operator. So showing that omega is continuous is equivalent to showing that T of omega is continuous. So we can show that for a commutative Hilbert quasi-star algebra that is unital, we need to assume that A0 is a Banach star algebra. And also we need to assume this technical condition, then omega is representable. If omega is representable, it will be bounded. This technical condition is, of course, verified in the case of the L2 spaces over C of I and L infinity. So there are other problems that we would like to investigate, and the first one is either to show that every representable functional is continuous, or eventually construct a representable functional that is not continuous. I have showed you an example of a continuous functional that is not representable, where we don't know anything about vice versa. And also we have given conditions which are strong on the elements of a quasi-star algebra to show continuity. So can we find a condition that depends on the functional considered? Maybe that can tell us if a single functional that is representable is also continuous or not. And can we use other theories or tools to understand, to study continuity of these functionals, other that the intertwining operators theory, And also we would like to know, in the more general case of locally convex quasi-star algebras, what happens. Of course, the Banach structure plays an important role in such investigation. I would like to briefly mention some applications that we have. So in this case, we have used sesquilinear forms and all the results that we had for full representability and star semi-simplicity to investigate derivations on quasi-star algebras. And we have studied similar results to the Bradley-Robinson theorem. So in this case, we need to assume that the Banach quasi-star algebra is star semi-simple, such that we have enough sesquilinear forms. And we have weakened the notion of derivation, of star derivation, but also the notion of star automorphisms, in the sense that we have considered a weak one. So in one direction, if delta is an infinitesimal generator of beta, then delta is closed. For the converse, we need to assume that the domain of the derivation is made of bounded elements. And also we need to assume further technical conditions such that to show that delta is the infinitesimal generator of beta. And the reason why we need these technical conditions is that we need to deal with the multiplicative property of beta as a group, and we know that we have problems with the multiplication. Anyway, such technical conditions are verified for the weak derivative in L2. The second application concerns the study of representability in the case of a tensor product. So we start with the unital Banach quasi-star algebras, and we consider a uniform cross norm on the tensor product. The reason why we want the cross norm to be uniform is because we need the tensor product of bounded operators to be bounded. So from the tensor to the factors, all the representability properties that we have seen, so full representability and star semi-simplicity, pass from the tensor to the factors, but for the vice versa, we need the tensor, the pre-completion tensor product to be a barred space, and also the properties pass from the factors only to the pre-completion. Unfortunately, the question about the completion is still open, and we don't have an answer yet. So I would like to briefly stop mentioning two examples, namely the tensor product of L1 with L1 with respect to the projective tensor norm that gives you a barred space. So that's an example that falls on this case. So it will give you a Banach quasi-star algebra. And if you consider L2 with itself completed with topology given by the Hilbert spaces, then you get again a Hilbert quasi-star algebra, and then you can apply all the results that we have seen before. So this was my last slide, and I wish to thank you for your attention.